Okay, so question 3 is asking about the polarity of dextrose, whether it's polar or nonpolar. And the information that we're given is that the solubility of dextrose in water is 909 grams per liter at room temperature. And 900 grams per liter that's a lot of grams that we can dissolve in a very small amount of water. And so the solubility of dextrose in water particularly is really high. And we always like to say in lab that like dissolves like. So if water, we know that water is polar here. And we know that dextrose is really, really soluble in water because this is a very, very high number. You can put a lot of dextrose in water at a very low temperature without heating it up to sort of facilitate that dissolution. So if we take all of that information together, we find that our dextrose molecule is also polar because of this like dissolves like relationship. So then question 4 is asking, what are the intermolecular forces in this glucose molecule when it interacts with water? So we're going to go back up to the structure here, which is the Haworth projection of the dextrose molecule. And we're going to look at what types of bonds we have and what could those intermolecular forces be. So right off the bat, we can see that we have a lot of these OH groups. And when we have OH groups, we're always going to have hydrogen bonding. Because that's always going to be present when a hydrogen is connected to a really, really electronegative atom like oxygen or nitrogen. So we can write hydrogen bonding here. And what we're also going to notice is that while it's a covalent molecule, this dextrose compound, it's actually a polar covalent molecule because there's a lot of asymmetry here. Those dipole moments, the partial dipoles, they don't cancel out because we don't have a symmetrical model. So in addition to hydrogen bonding, we're also going to have dipole-dipole intermolecular forces. And then pretty much every molecule that we're going to see in this class is also going to have London dispersion forces. And that's because these are induced dipole interactions, which happen on a very temporary scale. And pretty much any molecule can induce a dipole in another or get induced dipole from something else. So that's pretty much always going to be present when we're thinking about intermolecular forces. So now we're going to go back to the solubility that we talked about in question 3, because question 5 is asking if we take a solution of 90 grams of dextrose in 100 milliliters of water, is this solution saturated, unsaturated, or supersaturated? So we want to think about the solubility, which from question 3 is 909 grams per liter, which is the same as 1,000 milliliters. But in question 5, the volume that we're given is 100 milliliters. And so we're kind of comparing apples and oranges at the moment. So what we're going to do is linearly scale this solution of dextrose so that the volumes are equal, and then we can compare the grams a little bit easier. So to convert a volume of 100 milliliters into 1,000 milliliters, we're going to multiply by a factor of 10. So that creates 1,000 milliliters. And then whatever we do to the bottom, we also want to do to the top. So we're going to multiply 90.9 grams by 10, and that's going to give 909 grams per milliliter. And now what we can see is that this solution of dextrose and water actually matches the solubility limit for dextrose and water. And so that would make this a saturated solution. We're sort of at that limit. We've reached the maximum amount of dextrose that we can dissolve in water. So then number 6 says if you then take this solution, you cool it to 5 degrees from 25 degrees. So we're going pretty cold here. And the solution remains homogeneous. Would that be saturated, unsaturated, or supersaturated? And we actually find that this slow cooling below room temperature while still remaining homogeneous, so it's still all mixed together, there's no solid that's crashing out of the water at all. This is actually our definition of supersaturated. And then number 5 is asking about the D5W solution. So this is a little bit different than the other solution from question 5 here. So if we go back up to the information from the D5W solution, it's 5 grams of dextrose in 100 milliliters of water. So we're just going to write that again for the D5W. We have 5 grams over 100 milliliters. Is this saturated, unsaturated, or supersaturated? And so we want to compare it again to the solubility limit of dextrose in water just generally. And so that's 909 grams per 1,000 milliliters. And just like question number 5, we have a volume of 100 and a volume of 1,000. So we want to multiply this whole thing by 10 over 10 to get 50 grams in 1,000 milliliters so that we can directly compare the D5W solution to the dextrose solubility. And we find that this 50 grams is way under the 909 gram limit of solubility. So for question 7, the D5W solution is unsaturated. So now we're going to get into some more heavy math. So I just wanted to remind you all that there are 2 different solutions of this dextrose in water. And so those are going to be described either as D5W or the solution from question 5, which if you'll remember, that's up here, that's the 90 grams of dextrose in 100 milliliters, whereas the D5W solution is 5 grams in 100 milliliters. So just keep that in mind and pay attention as we're going through this to which solution the worksheet is talking about in each problem. So we're going to start off. Question 8 is asking about the mole fraction of water specifically in the solution described in Q5. And so to find the mole fraction, we're going to need our total formula for that is capital X, which is our symbol for mole fraction, and we're looking at water. So we need the moles of water as well as the total moles, which is going to be moles of water plus moles of dextrose. So the question 5 solution is 90.9 grams of dextrose and 100 milliliters of water. So we can start with finding the moles of dextrose. So we're going to start with that 90.9 grams. And then we're going to divide it by the molecular weight, just like we did earlier in this problem. And that's in units of grams per mole. And we find that that comes out to 0.504 moles of dextrose. And then we can do a very similar thing for the moles of water, but we're going to start with the volume that we're given. So that's 100 milliliters. And before we can use the molecular mass of water, we need to get out of these units of volume. And so the relationship that we have between units of volume and units of mass is our density. So we're going to use the density of water, which they're given as 0.997 grams per milliliter, and that makes these milliliter units cancel out. And then we can use our molecular weight of water, which is 1 mole over 18.015 grams. And that makes the grams unit cancel out and leaves us just with moles. And that turns out to be 5.53 moles of water. And so if we go back to our mole fraction equation, which is just parts over the whole, we're going to take the moles of water, which we calculated as 5.53, and then we're going to divide it by both of the mole values that we just calculated for the whole solution. So that's 5.53 plus 0.504, and when you plug that into your calculator, you get 0.916 as your mole fraction of water. So our next question, number 9, is asking for the molality of the solution of D5W. So the question that we just did was asking about the solution in Q5. Now we're going back to the D5W solution. And I do want to point out really quickly that molality is slightly different than molarity. So the equation for that, for molality, is moles of solute over kilograms of solvent. And in this case, the solute is our dextrose and the solvent is water. So we're going to first find our moles of solute. And so we're going to start with the mass of dextrose. And remember, this is the D5W solution, so that starts with 5.0 grams of dextrose. And we're going to divide it by our molecular mass, which is 180.156 grams per mole. And that gives us a really, really small number of moles. It's 0.028. And then to find the kilograms of solvent, we know that we have to start with the 100 milliliters of solvent. And just like we did in the mole fraction, we want to convert from milliliters to grams, and we're going to use the density of water to do that. So that's 0.997 grams per milliliter. And so that gets rid of milliliters, and now we want to go from grams, which we have here, to kilograms, because that's what's in our formula. And so we're going to say 1 kilogram is equal to 1,000 grams, and that will cancel out the grams. And this number turns out to be 0.0997 kilograms. So then if we go back to our molality formula, we're going to take the moles that we calculated and we're going to divide it by the kilograms that we calculated. And that turns out to be 0.28. And the way that we write molality is a lowercase m. So that's question number 9. Question number 10 is now asking about the molarity of the D5W solution. So we're still going to use the same numbers that we used in question 9, but now we want to look at the molarity, which is moles per liter. And so we can use the same number of moles as we did from question number 9. So that's 0.028 moles. And then we don't have to go through the whole process of using the density of water because it's already in units of volume. We just have to convert milliliters to liters. And we're going to use the relationship 1 liter is equal to 1,000 milliliters. And if you plug all of this into your calculator, you actually get 0.28. And this is molarity, remember from question 10. So we write that as a capital M. And so we actually find that the molality and the molarity of the D5W solution are identical when we're finished with all of the rounding. So question 11 continues to ask about the D5W solution, so just keep that in mind. But then it wants you to calculate the osmotic pressure of this solution. And the osmotic pressure, the symbol for that is this funky looking Greek letter, and that's equal to the molarity of the solution, capital M, times the gas constant, capital R, times temperature. But just one thing to watch out for, temperature should be in units of Kelvin. So we can start plugging things into our osmotic pressure formula. So we already know the molarity. We have that from question number 10. So we're going to plug that in. And then we're going to multiply it by the ideal gas constant, which is 0.0821. And then it has kind of funky units. It's liters, atmospheres, over moles, kelvins. And then we're going to multiply it by the temperature, and we're going to convert the degrees Celsius, which is 25 degrees, plus 273 approximately, so that we convert, this is the degrees Celsius to Kelvin conversion. And when we plug all of that into our calculator, we end up with approximately 6.9 atmospheres. And the way we get atmospheres is this molarity here, remember, is moles per liter. And so that cancels out the liters on top and the moles on bottom from the ideal gas constant. And then the temperature here is in Kelvin, so that's going to cross out with the Kelvin and the ideal gas constant, and we get just units of atmosphere. Now, if we go down to question 12, that's again asking about the osmotic pressure, but this time it's asking about the solution from Q5. And so it's the exact same calculation of osmotic pressure, which is equal to mRT, but we don't know yet what the concentration of that question 5 solution is. So we can calculate that really quick. We do know that we have 0.504 moles, and we get that from this calculation up here. Number 8 was also asking about Q5, and we already calculated the moles of dextrose, which is this really small number here. So we can use that down in question number 12. So we have the moles, and now we need the volume, and it's given to us as 100 milliliters. So we're just going to use that same conversion, milliliters to liters here. So that's 1 liter over 1,000 milliliters. And if we plug all of that into our calculator, we get 5.04 molar as the concentration. So we're going to take that value, we're going to multiply it by the ideal gas constant again, which has those same funny units. And then we're going to convert the temperature into Kelvin, and it's still at 25 degrees Celsius. So when you convert it to Kelvin, that becomes approximately 298 Kelvin. And so once we plug all of that into our calculator, we get about 123 atmospheres as our answer. And what you'll notice is that 123 is so much more so much more pressure than the osmotic pressure of the D5W solution. And that's going to come in really handy when we go down to the last question, question 13, that's asking, what happens if you use this incorrect solution of dextrose as an IV solution in your patient's bloodstream? What's going to happen? And it gives us the information that the osmotic pressure of human blood is about 7.5 atmospheres. And that's very, very close to the D5W solution, which has about 6.9 atmosphere of osmotic pressure. So you can imagine that if you put into someone's bloodstream this solution with 123 atmospheres of pressure, that there's going to be a really big difference and probably some not so great biology things that are happening here. And when we think about osmotic pressure, that has to do with two different solutions across a membrane. So we're just going to draw an arbitrary membrane here. And we have one solution of approximately 7.5 atmospheres. And you can think of this as the osmotic pressure in your typical bloodstream as well as your blood cells. And then on the other side of the membrane is this 123 atmosphere osmotic pressure. And if that's coming from the IV, that's going to be the pressure in your bloodstream. So now there's this huge difference between your blood cell osmotic pressure and your bloodstream osmotic pressure. And the thing about this membrane is that it does not allow those dextrose molecules to cross the membrane, but it does allow water to cross. And so we want to try and equalize these two pressures, because this is a really bad situation for your body to be in. And so there's more dextrose molecules on the left here. And so we want to try and match our typical blood cell pressure. So the water is going to travel from your blood cells into your bloodstream. But what happens then is that your blood cells are going to shrink because water is leaving those cells to compensate for the higher concentration in your bloodstream. And that's going to cause them to shrivel because there's no water that's replacing them, because it has to all travel out of your bloodstream, out of your blood cells into your bloodstream to lower that pressure. So that's going to cause your blood cells to shrivel, which would be pretty bad for your body. And that is a process that's called crenation. So I hope that this explanation of the worksheet answered some lingering questions if you had them, but please feel free to reach out if you're still a little bit confused or you want me to clarify a few different things or explain them in a different way. But other than that, have an awesome day.